Okay, and then we can move on to a slightly different variation. I know that a lot of these look alike, but they all demonstrate something that's fairly similar. So let's suppose that we want to evaluate the sum from n equals 3 to infinity of 3 times 2 to the 2n plus 1 over 3 to the 4n. All right, so this is how we want to simplify this. This is n equals 3 to infinity of, this is 2 to the 2n plus 1 is equal to 2 to the 2n times 2 to the 1. That's how the law of exponents works there. So this is going to equal 3, 2 to the 1 is 2, times 2 to the 2n over 3 to the 4n. And then just once we've done that, once we've dealt with this plus 1, just as we did before, this is going to become 6 times, put the 6 out here, 6 times 4 squared, let me write it this way, not 4 squared, 2 squared to the n over 3 to the 4th to the n, which once again is giving us a common ratio of 4 over 81 to the n. And now, of course, we have, that's m, that's c, and that's r. It's very similar, except it was c that was different this time. So the sum is just going to be 6 times 4 over 81 to the third over 1 minus 4 over 81. And that gives an answer. Okay, so there's yet another example. Let's see what's coming up next. Does sum from n equals 0 to infinity of 2 to the n plus 3 to the n over 4 to the n converge or diverge? If it does converge, then find the sum. Well, doing a little algebra, of course, everybody knows that 2 to the n plus 3 to the n is equal to 2 plus 3 to the n, right? No, it's not, but I can't tell you how many times I read stuff like that, even among Calc 2 students. So that's really the error here, because if you did that, you would conclude that what we were looking at was, I don't really want red there. This is more a purple situation. Um, what we'd be looking at is 2 plus 3 to the n over 4 to the n, which is the sum of 5 over 4 to the n, and you'd say, well, wait a minute, if that's the common ratio, then it's great, it's outside of the range -1 to 1, so this series diverges. But this is not the correct way to do this. The correct way to do it is to say that the sum from n equals 0 to infinity of 2 to the n plus 3 to the n over 4 to the n is equal to the sum from n equals 0 to infinity of 2 to the n over 4 to the n plus 3 to the n over 4 to the n. So that, since summations are linear, we can break this up and just make this the sum from n equals 0 to infinity of 2 over 4 to the n plus the sum from n equals 0 to infinity of 3 over 4 to the n. So that's going to come out to 1 over 1 minus 2 fourths is just 1 half, plus 1 over 1 minus 3 fourths. So that's going to be 1 over 1 half plus 1 over 1 fourth, which is 2 plus 4, which equals 6. So that sum comes out to 6. Let's show the entire question here. There we go. All right. So we've got that example. Slightly different example. I'll just show you how to set this up. This one, it's similar, but here the 2 doesn't have an n in front of it, so this is going to be n equals 0 to infinity of, this is going to come out to is 2 over 5 to the n plus 3 to the n over 5 to the n. So the way that this one breaks up is it's going to be the sum from n equals 0 to infinity of, that's 2 times 1/5 to the n plus sum from n equals 0 to infinity of 3/5 to the n. So in this case, we know that m is 0 for both of these integrals. Sorry, not integrals, for these summations. In here, we have c is equal to 2 and r is equal to 1/5. Here we have c is equal to 1 because there's nothing being multiplied by the 1/5, and we have r is equal to 3/5. So this summation comes out to 2 times 1/5 to the 0 over 1 minus 1/5 plus 1 over 1 minus 3/5. So that comes out to 1/5 to the 0 was 1, by the way. So that's going to be 2 over 4/5 plus 1 over 2/5. So that equals 2 times 5 over 4 plus 5 over 2. That's going to be 10 fourths plus another 10 fourths. I believe that's right. Actually, we can do it. It comes out a little nicer if I just say this is going to be 5 halves plus 5 halves, and that equals 5. Okay, so let's finally do the last example in our medley of geometric series. We have evaluate the sum from n equals 0 to infinity of 7/6 to the n. Now many people say, oh, I've mastered that formula. Here's r, here's m, and of course there's the constant factor of 1, so surely this must equal just 1 over 1 minus 7/6, which is 1 over negative 1/6, which is negative 6. The problem with this, of course, is it's a very beautiful solution. It just happens to be wrong. The mistake here is not realizing that 7/6, the absolute value of 7/6 is greater than or equal to 1. It's not in the range where the series converges. And a little thought shows that what you're doing is you're adding up 7/6 plus 49/36 plus dot dot dot. In other words, we keep adding up fractions that just keep getting to be more and more than 1. And the idea that they somehow come out to a negative number like negative 6 just doesn't make any sense. So this series diverges. It can't be evaluated.